We hear the news constantly now, and it is genuinely dizzying. Multimodal large language models, MLLMs, are achieving levels of competence that feel, well, straight out of science fiction.
They really do. I mean, they can process these complex charts, synthesize massive amounts of data, and answer questions that would challenge a university professor.
Totally.
It's true. When you look at high-level knowledge benchmarks, like MMMU, you see these frontier models like Gemini 3 Pro scoring 92.8% on college-level questions.
92%.
They're conquering PhD-level geometry, complex chemistry, nuanced literary analysis with just remarkable ease. They're practically passing humanity's last exams.
That level of competence is genuinely astonishing. It makes you think, okay, we are right on the verge of AGI, artificial general intelligence. But here's the pivot for this deep dive, and this is where it gets really interesting. If an AI can handle advanced quantum physics, what happens when you give it a visual task designed for, say, a preschooler?
It's a great equalizer, that question. What about a simple visual puzzle, like matching a cartoon penguin to its exact shadow, or tracing a line through a basic maze?
The surprising and frankly baffling answer, based on the new research introducing the BabyVision benchmark, is that these hyper-advanced systems struggle.
They struggle severely.
They consistently fail at visual tasks that human children, even kids as young as 3, solve effortlessly, probably while humming a tune.
And that's the critical sort of inverted gap we're exploring today. How can a model be an expert scientist, fluent in calculus and ancient history, but a poor visual observer? So poor, it can't complete a simple join-the-dots exercise.
Our mission for this deep dive is to go inside the BabyVision benchmark to identify exactly why these super smart computers are failing the kid test. We're exploring that gap between frontier AI, visual reasoning, and fundamental early human vision.
And we're going to look specifically at the performance data. The benchmark was explicitly designed to assess core visual abilities, totally independent of linguistic knowledge. And the core finding is stark. The strongest frontier model they tested, Gemini 3 Pro Preview, scores 49.7% overall.
Okay, wait. 49%.
Just under 50. And that puts the best AI model available today approximately 20 percentage points behind the typical accuracy of a 6-year-old human.
20 points behind a 6-year-old. Okay, that is the baseline we need to keep in our minds. Let's start by defining what kind of intelligence BabyVision is even trying to measure. What are these fundamental skills we develop so early?
Well, we call it early vision, and it's the nonverbal foundation for everything we perceive. Human visual understanding emerges remarkably early, months before language, months before any formal symbolic reasoning.
Right.
Think about it. An infant can already discriminate between shapes, track a moving object across a complicated background, and infer depth within the first few months of life. These are atomic visual competencies.
They're like the default operating system for visual reality. You don't need training in abstract geometry for this. It just emerges from interacting with the world.
Exactly. And these skills form the critical, non-negotiable foundation for all the later high-level cognitive functions, everything from abstract math to complex motor planning. If you can't maintain the identity of a continuous line, how can you draw a coherent graph?
So the BabyVision benchmark aims to bypass all that high-level, language-heavy knowledge, all the stuff MLMs are usually trained on, and go straight for the perceptual primitives. So tell us how the benchmark is structured.
It contains 388 questions across 22 subclasses. And crucially, the tests minimize reliance on descriptive language. The model isn't being asked to describe the image. It's being asked to use its perception to solve a pattern or a path. It focuses on 4 core domains of visual perception.
Okay, domain 1.
That's fine-grained discrimination. This is the ability to spot subtle differences between visually similar objects. Is this shadow exactly the same, or is there a tiny difference in the cursor?
Domain 2.
Visual tracking. This is all about maintaining the identity of an object or a continuous line through intersections or occlusions, essential for something like a maze.
Okay, domain 3.
Spatial perception. This is the crucial 3D component. Inferring hidden volume, mentally rotating objects, or imagining what a piece of folded paper will look like when you unfold it.
And the last one.
Visual pattern recognition. And that's the ability to induce abstract relational structures from examples. So understanding rules like rotation, mirroring, or simple geometric logic.
Okay, so let's look at the scorecard. Because once you understand what they're testing, the performance gap is just stunning. We know the best AI model scored just under 50%, What about the humans?
The adult human testers scored 94.1% accuracy overall.
Near perfect.
Near perfect competence on these foundational tasks. And remember, the scores for the children's age groups follow a smooth developmental curve. The average 3-year-old performs significantly better than the open source models.
I'm looking at the chart here. The best open source model, Qwen 3VL 235B Thinking, scores only 22.2%. That's a massive gulf between state-of-the-art OpenAI and a preschooler.
Yeah, the research refers to this phenomenon as an inverted profile of competence. These models excel at the high-level, knowledge-intensive benchmarks, the things that require years of formal education, but they fundamentally lack the atomic visual competencies that every child develops just by playing and exploring.
It's the ultimate paradox of modern AI. It's like having an encyclopedic memory but suffering from extreme visual agnosia. You can describe what a chair is, but you might struggle to identify one in poor lighting.
That's a great way to put it.
It strongly suggests that scaling up linguistic knowledge, no matter how much compute you throw at it, doesn't automatically grant you robust, grounded visual perception.
And when we analyze the results across the subdomains, the failure isn't random. On the BabyVision mini subset, which is strictly vision-centric, the strongest AI, Gemini 3 Pro Preview, while it's better than the 3-year-olds, it consistently stayed about 20 percentage points behind the 6-year-olds, across the board.
The foundational visual skills are just structurally absent.
They are.
This is where we need to get specific. Let's dive into the 4 systematic failure modes identified in the source. If they're failing systematically, that tells us something fundamental about the architecture. You noted that the largest failures appear in visual tracking and spatial perception.
Right, so the first failure mode is the loss of fine-grained detail. This shows up in tasks that require high-resolution comparison, like find the same or find the shadow. The system confuses things that look almost identical.
Give us the penguin example.
Okay, picture a specific cartoon penguin in the center. Around it, you have 5 slightly different shadow options. A human, or a 6-year-old, can easily spot the correct silhouette by comparing subtle geometric cues, the precise curve of a wing, the angle of the beak, the tiny difference in the shape of a foot. They perceive continuous geometry.
But the AI doesn't.
Precisely. The human baseline for find the same is 80%, yet the best proprietary model only managed 26.5% accuracy.
Wow.
And the reason is, the models are attempting to discretize continuous shapes into what the researchers call lossy linguistic tokens.
Okay, let's unpack that term. Lossy linguistic tokens. Why would an MLLM do that?
Because MLLMs are primarily designed to optimize for text, for knowledge retrieval. When they get a visual input, they often compress that image down into a sequence of tokens, basically small chunks of data they can attach words to, before they even start reasoning.
So it's like saving a high-definition photograph as a very, very small JPEG file.
That's the perfect analogy. So if the model gets the visual input of the penguin, it doesn't process the exact curvature. It processes maybe short beak, round body, small wing.
Right, these descriptive features.
Yes. And this compression creates a resolution gap. Fine spatial structure, like the subtle difference between 2 shadows, is literally flattened and lost. This forces the model to reason through a low-fidelity descriptive proxy, which makes those micro differences indistinguishable.
The subtle differences are sacrificed just to fit the visual input into the text stream.
Exactly.
That immediately leads us to the second major failure, the loss of manifold identity, which happens in the visual tracking domain.
This sounds like a topological failure.
It is. This happens in mazes, line observation, and the connect the lines tasks. Imagine a tangled drawing where a crocodile, a moose, and a bunny have their lines crossing and overlapping on the way to their homes below.
Oh, I remember those puzzles as a kid. You had to be really careful to keep your eye on the line and not switch over at a crossing. That ability is called contour integration, and a human or a 6-year-old uses it to lock onto a curve and track that path persistently, ignoring the noise of the intersection. MLLMs, however, they repeatedly switch tracks at crossings. They reveal a fundamental inability to separate overlapping signals and maintain that continuity.
Wait a minute. If the model can't maintain the identity of a continuous line, that's a massive breakdown in how it simulates physical reality, isn't it? Its whole representation of space isn't robust.
Absolutely. The source notes that some models scored near 0 on the line's observation task. That translates to a complete inability to trace curves through intersections. They might know conceptually what a path is, but they can't perceptually follow it.
That inability to maintain spatial coherence brings us to the third failure, which is failure of spatial imagination. This is crucial for those spatial perception tasks where you have to infer hidden structure.
Right. Tasks here include count 3D blocks and paper folding. In the block task, you see a stack of blocks. Some are visible, some are hidden, and you have to infer how many blocks are needed to support the structure and then count the total.
So this requires mentally simulating what you can't see, the blocks that are hidden by other blocks.
Exactly. And the systems fail uniformly. Count 3D blocks is challenging for all of them, with the best score only being 20.5%. MLLMs struggle with occlusion and viewpoint variation because they don't perform nonverbal mental simulation, the way a human does when they mentally rotate a Rubik's Cube.
So instead of rotating the object in a mental 3D sandbox, what are they doing?
They attempt to approximate the 3D state through descriptive logic. They try to summarize components with language. There's a block on the left and a block behind that. But as the complexity increases, language acts as an insufficient coordinate system for volumetric constraints.
So if I asked you to describe the precise geometry of a complex sculpture using only words, you'd fail.
You would. And the machine is trying to use a word processor to do the job of a geometric rendering engine.
That's a great analogy. They're trying to use descriptive words to substitute for a physics-compliant visual model, and it collapses when the input requires true inference of hidden volume.
It collapses when the input requires nonverbal reasoning.
And finally, the fourth failure of visual pattern induction. This deals with recognizing abstract relational structures like rotation or mirroring.
Here we see comparative strength, but the models still show deep flaws. They perform much stronger on discrete tasks like logic patterns and rotation patterns, where symbolic reasoning helps. For example, one model scored 70% on rotation patterns, likely because rotation can often be simplified to a simple symbolic command like turn 90 degrees.
So where does the failure appear in pattern recognition then?
They struggle significantly with overlay patterns and mirroring patterns. The core issue is that they often fixate on what the researchers call spurious surface correlations. They might notice that option A has the same color as the prompt, the same texture, and choose it based on that superficial thing, rather than correctly inducing the underlying structural logic, like this shape is the mirror image of that one.
They mistake the style or the superficial appearance for the underlying geometric rule.
Precisely. They're pattern matchers, but they struggle to abstract the relational rule governing the pattern.
So we've identified 4 distinct but related ways they fall apart. Losing fine details, inability to track a continuous line, lacking 3D mental rotation, and mistaking appearance for abstract rules. If we connect these, the unifying factor has to be the verbalization bottleneck.
That is the organizing principle behind this whole failure profile. As we discussed, current MLMs translate visual inputs into language representations, into tokens, before reasoning can even happen. This is done to leverage the massive reasoning power of the language model component.
But this process discards critical data.
It discards geometric and fine-grained information that is fundamentally undescribable in language. The precise curvature of a boundary, the exact spatial relationship of 2 lines at an intersection, this kind of information is just lost in compression. Language is simply an insufficient coordinate system for continuous spatial constraints.
The AI is optimizing for conversation, not for geometry.
It is.
So if a picture is worth 1,000 words, the MLLM basically throws away 999 of them just to fit the image into its text processor. And that lost data is the foundation of early vision.
It's the fidelity we need for grounded intelligence. And we even have fascinating experimental evidence from the source that supports this. Researchers tried to boost performance using something called reinforcement learning with verifiable rewards at RLVR on one of the models.
Right. RLVR is a technique designed to encourage structured, language-driven reasoning. It helps generate better thinking tokens or internal monologues before the final answer. So the expectation would be a solid performance jump.
And they did see an overall accuracy gain on the benchmark. It improved by about 4.8 points. The model got better at certain symbolic tasks because its internal monologue was improved.
But what's the catch?
The catch is when the researchers look specifically at the visual tracking category, the maze and line tracing tasks, RLVR, yielded little to even negative improvement.
Wow.
In some cases, the model became worse at tracing lines.
Wait, that's a profound result. The training method designed to enhance language-mediated reasoning failed to fix the visual tracking issue.
Exactly. Because those tracking tasks are the ones least amenable to verbalization. The AI can now write a more coherent, structured sentence about the maze, but it still can't follow the line on the visual input itself because that visual data was corrupted upstream by the verbalization bottleneck. The problem is perceptual, not linguistic.
This observation is what led the researchers to look beyond text answers, right? Using a generative extension called BabyVision Gen. Instead of asking the model for a text response, they ask it to solve the puzzle visually, similar to how a human might draw on the page.
It tests the idea of visual externalization. I mean, think about it. When a child solves a maze, they often trace the path with their finger or a pencil. They are thinking in visual space, not generating turn-by-turn text directions. So BabyVision Gen has 280 questions where models have to annotate the image, maybe trace the path in red, or mark the correct shadow.
So what happens when we force the MLLMs to use a visual output? Do they suddenly unlock that nonverbal intelligence?
The results are still mixed. Generative models like NanoBanana Pro achieved around 18.3% overall accuracy, which is low, sure, but they show promising signals. They sometimes exhibit fragments of human-like visual thinking by drawing temporary annotations on the image. You can see examples where they start to trace a line.
So we're seeing emergent visual behavior, a bit like the amazing physical dynamics we see in those frontier video generation models like Sora 2 or Veo 3.
Precisely. They can start to act visually, which suggests the generative process itself can encode physical or spatial reasoning. However, the massive limitation remains. Even these models score 0% accuracy on continuous tracking tasks, like the maze.
Still zero.
Still zero. Current generation architectures just can't maintain spatial coherence over extended sequences. They still lose track of the line after one or two intersections, just like the non-generative models.
So what this research implies then is that for AI to genuinely acquire this grounded visual intelligence, this 6-year-old level of competence, we need architectural innovations that completely bypass that verbalization bottleneck. The model has to learn to think in visual space.
It must maintain visual fidelity throughout the entire reasoning process. We need models that process and manipulate geometry natively, rather than treating geometry as some side effect of language optimization. They need to internally simulate physical dynamics, trace paths, and highlight regions within the visual medium, not just describe them with text tokens.
That's a fundamental challenge. It means we need to redesign the internal architecture to be grounded in perceptual reality, not just linguistic abstraction.
It forces us to acknowledge that high-level human-style intelligence is built upon layers of foundational, low-level perception. You can't just skip the baby steps.
So what does this all mean for you, the learner? You see headline after headline about AI competence. How should this new understanding from BabyVision change how we evaluate these systems?
I think it means we have to apply a lot of caution and critical analysis to AI claims. An MLLM can analyze a complex economic chart that's a high-level language-heavy task that uses its encyclopedic knowledge, but it might struggle to trace the simple lines used to create that chart or count the 3D blocks that form its bar graph. High-level knowledge is easy for these systems because it's encoded in text. Foundational visual primitives, the things a 6-year-old masters automatically, are fundamentally hard because they're nonverbal.
We can't confuse impressive high-level reasoning with fundamental visual competence. It highlights a critical distinction. AI intelligence, as currently built, is largely top-down from language, not bottom-up from perception, which is the complete reverse of human development.
And that leads us to the final provocative thought. Developmental psychology shows that children learn to reason about their world by manipulating it. They externalize visual reasoning by drawing, by stacking blocks, by acting, long before they can verbalize solutions. If advanced AI struggles so severely with the visual basics, what essential nonverbal knowledge is foundational to human intelligence that we haven't yet learned how to successfully teach a machine? Should we be prioritizing those baby steps and designing visual-first intelligence before we demand conversational mastery?